Silicon. That's where we left off. In the last episode, we watched 100 years of history collapse into one afternoon. 3 physicists in New Jersey, a tiny piece of germanium, 2 gold contacts, and a signal that came out larger than it went in. The transistor, born on the 16th of December, 1947. But we didn't answer the most important question. Why germanium? Why silicon? What is it about these materials that makes them behave so differently from copper or rubber or glass? What property do they have that makes them not just conductors or insulators, but something you can actually control? That's what this episode is about. To understand silicon, you need to understand where it lives in the universe. And that means a brief stop at one of the most important diagrams in all of science. The periodic table. Every element that exists, every type of atom, is arranged in this table, not randomly. The arrangement means something. Elements in the same column behave similarly. Because the column tells you something specific about the atom. It tells you how many electrons are in its outermost shell. And that outermost shell is everything. Let's go back to the atom for a moment. From episode 1, every atom has a nucleus at the center with protons and neutrons packed inside it. And electrons orbit around the outside. But those electrons don't orbit in one big cloud. They sit in layers called shells. The first shell closest to the nucleus holds at most 2 electrons. The second shell holds up to 8. The third also 8. Each shell fills from the inside out. The innermost shell fills first, then the next, then the next. And the electrons in the outermost shell, the ones furthest from the nucleus, are the ones that interact with the world. They're the ones that bond with other atoms. They're the ones that carry current. They're the ones that define what a material is. These outermost electrons have a name. Valence electrons. Now, take copper. Copper is a conductor. In episode 1, we said electrons in copper are loose. They drift freely from atom to atom. Here's why. Copper has 29 electrons. Most of those shells are full. But the outermost shell has only 1 electron. 1 lone valence electron. And a single electron in an outermost shell is held very loosely. It barely belongs to the atom. It can wander freely into the space between atoms. It becomes a free electron. That's what conduction is. Free electrons drifting through a material. Now take rubber. Rubber is an insulator. Its electrons are not free. They're locked in place. Why? Because in rubber, and in similar materials, the outermost shells are full. 8 electrons. Nothing missing. Nothing extra. Everything tightly bound to its atom. No free electrons. No conduction. The fuller the outermost shell, the tighter the grip. So where does silicon fit? Silicon is element 14. It has 14 electrons. 2 in the first shell, 8 in the second, and 4 in the outermost shell. 4. Not 1, like copper. Not 8, like a full insulator. Exactly in the middle. 4 valence electrons, and here's what silicon does with those 4 electrons. It shares them. A silicon atom looks at its 4 neighbors, 4 other silicon atoms, and each pair of atoms shares 2 electrons between them, 1 from each atom. Each atom ends up with 8 shared electrons around it. A full outer shell, a stable, tightly bound structure. These shared electron pairs are called covalent bonds, and pure silicon bonded this way forms a regular repeating crystal lattice. Every atom in its place, every electron paired up, every bond satisfied. And because every electron is tied up in a bond, there are no free electrons, which means pure silicon is a very poor conductor. It barely conducts at all. So why is it useful? Because it's right on the edge. Copper has too many free electrons. It conducts and you can't control it. Rubber has none. It blocks always. Silicon has just enough structure that it normally blocks, but just enough freedom that you can push it either way. You can change silicon, precisely, deliberately, by adding other atoms to it. This process is called doping. Here is the key idea of doping. Pure silicon has 4 valence electrons and forms 4 covalent bonds. What if you replace some of the silicon atoms, not many, just a tiny fraction, with atoms that have a different number of valence electrons? Let's try phosphorus. Phosphorus has 5 valence electrons. You place a phosphorus atom inside the silicon lattice. It forms 4 covalent bonds, just like silicon does, but it has 5 electrons to work with. 4 of them go into the bonds. The 5th one has nowhere to go. It's extra, unbound, free, it drifts. You've created a material with free electrons, not because the atoms are loosely held like in copper, but because you deliberately injected an extra electron. This is called N-type silicon, N for negative, because the charge carriers are electrons which are negatively charged. Now let's try the other direction. Take boron. Boron has 3 valence electrons. You place a boron atom inside the silicon lattice. It tries to form 4 covalent bonds, but it only has 3 electrons to contribute. One bond is incomplete. There's a missing electron, an empty space where an electron should be. This empty space is called a hole. And here's the strange but important thing about holes. They behave like moving particles. When an electron from a neighboring bond slides into the hole moves to where that electron was. Then another electron fills it from the next bond over. The hole keeps moving in the opposite direction to the electrons. If electrons carry negative charge, holes behave like positive charge carriers. This is P-type silicon, P for positive. 2 types of doped silicon. N-type, extra electrons, free to move. P-type, holes, which also move. By themselves, each type is just a slightly better conductor than pure silicon. But what happens when you bring them together? Place a piece of N-type silicon directly against a piece of P-type silicon. The boundary between them is called a P-N junction. And the moment you create that junction, something remarkable happens. Even with no voltage applied, no battery, nothing connected. The free electrons on the N side are right next to the holes on the P side. Electrons near holes, fill them. Electrons diffuse across the junction, from the N side where there are many, to the P side where there are holes waiting. As electrons leave the N side, that region becomes positively charged. As electrons arrive on the P side, that region becomes negatively charged. A thin zone forms at the junction where all the free carriers have annihilated each other. No free electrons, no holes, nothing to carry current. This zone is called the depletion region, and the charge difference across it, positive on the N side, negative on the P side, creates an electric field, a built-in voltage, sitting right there at the junction. Even with nothing connected, that built-in field stops more electrons from crossing. A balance is reached. The junction is in equilibrium. Now connect a battery. If you connect positive to the P side and negative to the N side, you're pushing in the same direction as the natural movement. Electrons on the N side are pushed toward the junction. Holes on the P side are pushed toward the junction. The depletion region shrinks. The built-in field weakens, and eventually, electrons flow through. Current flows. This is called forward bias. The junction is open. If you flip the battery, positive to the N side, negative to the P side, you're pulling electrons away from the junction on the N side, pulling holes away from the junction on the P side. The depletion region widens. The built-in field gets stronger. No current flows. This is called reverse bias. The junction is closed. Forward bias, current flows. Reverse bias, current blocked. That is a switch, a one-way valve for electrons. It lets current through in one direction and blocks it in the other. If you attach metal contacts to each end of a P-N junction and put it all in a small package, you have a component, a real usable electronic component. That component is called a diode. You've already met the diode in episode 2 when Fleming built his thermionic valve. That was a diode made of glass and vacuum. This one is made of silicon. 2 layers, 1 junction. No moving parts, no heat, no vacuum. It fits on the tip of a needle. And it was the moment engineers understood how to build the diode from silicon that the real story began, because a diode only does one thing, allow or block. But what if you had 3 layers instead of 2? What if you had 2 junctions instead of 1? What if you could use one electrical signal to control another? That is the transistor. In the next episode, we're going to go inside it completely. We'll look at the 2 main types, the BJT and the MOSFET. We'll trace exactly how a small voltage at one terminal controls a large current at another. We'll see how the P-N junction goes from a valve to an amplifier to a switch that can fire 1 billion times per second. And we'll see how that single structure gets printed, not one at a time, but billions at once, onto a piece of silicon the size of your fingernail, the transistor.